So I'll be discussing a file called checkDistance, which is in the folder allow of GameLogic. The allow folder contains several different files with a check prefix, all of which spit out a Boolean condition which sum together to permit a piece to move. These conditions include checkDistance, which checks if a piece is allowed to move in said orientation, such as a rook only being able to move horizontally or vertically, and a bishop only able to move diagonally. And checkColor, meaning the square you will arrive at either contains a piece of the opposite color, which would constitute a capture, or it is blank. CheckDistance was an interesting problem to solve because the coordinates for every single piece is a 6-bit number. 3 bits for the x-coordinate and 3 bits for the y-coordinate, of which we can look at all the numbers from 0 to 63. So initially the group did some arithmetic, and we found that by just, for example, adding or minusing 8 or adding or minusing 1, we're able to move a rook up and down and side to side. But that actually generated a problem where if rooks were on the corner, they were actually able to loop around to the next row because it's actually one continuous array of numbers. So we had to look at different ways to qualify this vertical and horizontal movement, along with all the other pieces for bishops doing things diagonally and knights being able to move in L shapes. What we came up with, I thought, was a very interesting solution, which is if you look at the bishop portion, you'll see that it is very similar to the rook portion for a very specific reason. We found that instead of looking at adding or minusing 7 or adding or minusing 9, well, instead of looking at these numbers very specifically, we have an additional condition, which is to look at if the rate of change in the y direction and the x direction is the same. Because we're moving in a pure diagonal, that is to say there's a 45-degree angle every time we go up, that gradient, that slope, is 1. So we can actually shift the bottom side of the fraction to the other side, and that's what you see here. We see if delta y is equal to delta x, this is constituted by a valid movement of y, and that would eliminate any sort of looping around motion. This is actually modeled in a Google Sheet that we made in order to properly predict and understand the behavior of this sort of looping around that the arithmetic created. So
for us, this was a part of our code we weren't sure we were going to be able to get done within the span of this project. It's very Verilog, but we were passionate to do it as it is a very critical part of the game. You can't win if you don't have checkmates and stalemates. And so I'm going to go over how we attempted it and how we were able to succeed and where we weren't able to as much. So it's all driven by king states. This finite state machine handles it's 2 finite state machines, handles the current state of each king, whether they're in stalemate, check, checkmate, or they're just chilling. And that works very closely with checks if you're in check, and as well as you'll see check allow works pretty closely with it, as well as these scans, which I'll explain in a moment. These are all currently in our unimplemented folder. You'll find this in the Verilog section of our repository. This is because we were unable to get them fully functioning within the rest of our code. However, we were able to make very significant progress on them, which you'll see in just a moment. This is the top of our finite state machine here. This is king states, and this handles the state of both the kings. So you can see it does so with a couple inputs, those inputs being a W and W. Now what are those? W is whether or not one of the adjacent squares to your king is in check with an opposing opponent's piece, and then AW is whether or not that's an allowed move for the king given. So we gather those 2 values, and then we run our state machine. And starting off in a safe state, we move to check if check. If not check, then we move back, and then if all the surrounding spaces are also checked, no other moves, you go to checkmate. It's very similar logic actually with stalemate. We found that stalemate is just checkmate but without being in check originally. And so it was pretty easy to copy and paste that code twice for each of the state machines and just ease it in that manner. A couple other files we had that I think are cool to go over. Scan straight, scan spots, scan diagonal. These all work very similar. I'll just go over scan straights while I have time. What scan straights does is it goes down a given row or a given column, and it scans to see what the closest piece is to your current piece that you're checking. And from that, you can gather if it's an enemy piece. You can gather perhaps if it's a rook, an enemy rook. You know you're in check because it's attacking you. There's nothing in between you and it. And we use this both for checking our path when we want to know if a piece can move, and as well as checking if you're in check.
I'm going to be talking about our module named Build Board, which is responsible for constructing and updating our chessboard. Our output is a 256 bits, which represents the chessboard. Then we have our local parameters that define constants, and each one represents a different chess piece and also colors. Then we have an always block that it is the main logic of this module, which is going to set up and update the chessboard. Of the game, then our module is going to begin setting up the board. It starts with the top row and sets up all of the black pieces. Then it goes on to the second row, which is more black pieces. And then the second, the third, the fourth, and the fifth row are all empty. And then the sixth row and the bottom row are all of the white pieces. And then finally, we have an if statement that every time there is a board change, then this will automatically update the chessboard.
Is Rohan. I'm just quickly going to talk about the VGA code, especially that's what I worked on in this project. So we start off with in the first few lines, just store the colors that are required to be displayed on the VGA, and that's we just store them as parameters, so it's easier to call upon later when we need them. Then next, from lines 46 to 54, we just store the data of the pieces and also the artwork of the pieces required. I'll get into the artwork a bit later. After that, we use a clock divider to divide the board's clock into a 25 megahertz clock to power the VGA, because that's what's required for the VGA. And we call upon the VGA generator to set up and initialize the VGA, which runs at a 640 by 800, a 640 by 480 resolution, which I'll get into right now. Our generate loop over here just stores our massive 256-bit board array into a 64 by 4-bit array in a way that pieces 0 would correspond to the top left square on a chessboard, whereas pieces 63 would correspond to the bottom right square on the chessboard. The 4 bits in each square store the color of the piece and the characteristic of the piece. We'll just go through lines 130 to 231. This is where it gets interesting. So once we have all the information about the pieces, we need a way to display it efficiently on the board. So this is what we chose to do. So we realized that the VGA display runs at a 640 by 40 resolution. So we decided to use 400 pixels by 400 pixels on the screen, which run in this manner, where the black box is a 640 by 480. The blue board over here is 400 by 400, and that gives you the location of the pieces. And the green box, which is highlighted over here, is a 50 by 50 pixel box, which we then split into an 11 by 11 box in this way so we can easily store our pixel art. This is what a black pawn would look like on our board. So this way it's easier to store that when the 11 by 11 section it has a 1 in it, that's when you color it, and when it's a 0, you just use the color of the board. This section here runs through how the pawn would look like on the board. So as we could see over here, this is what our artwork is. We start off with converting our 121-bit pawn array, which is stored over here, into an 11 by 11 box as such in the first three, in between lines 377 and 379. Then we call upon the board in the way that I said. When it's 1, you color it the color of the piece, and when it's 0, you color the remaining square, whether if it's a dark square or a light square. We utilize a similar function for our timer on the top left and top right, and the text which displays whose turn it is on the board, except instead of a 50 by 50 box, we just use a 10 by 10 or pixel array, which can, again, in a similar manner, we just use pixel art to correspond the letters to the colors that we want and how it would display on the VGA. Finally, we assign the colors. Over here, we can also see that we have current color as a variable, which is a 12-bit variable, which corresponds with the 12-bit color palette that our VGA provides us with. At the end, we assign the red VGA, green VGA, and blue VGA to 4 bits of the current color variable. The parameters that were mentioned at the start correspond in the same manner to the red, green, and blue VGA.